In this video we're going to look at a mathematical technique for analyzing nonlinearities in our oscillators, which is called a describing function. This is just a glimpse of the world of nonlinear control theory, which is full of really fun math and modeling. However, I'm picking this particular technique because it can give you some insight about the amplitude of oscillation and about whether an oscillation is sustained. We need to do describing function analysis because all practical oscillators are nonlinear. A linear system with two poles on the j-omega axis would oscillate forever if you kicked it with an impulse. But a second impulse would create another oscillation that's stacked on top of the first one. And there's no reason that it will. Further, there's no reason that a purely imaginary system would start up of its own accord and reach like a big oscillation. Random thermal disturbances would be present and they'd stay forever, but they'd be small. So when we make oscillators, what we see is they start themselves up, grow to a large amplitude, and then self-sustain, which is different than a purely linear system. So that behavior can be tracked back to nonlinearities in the amplification elements that we use. Any amplifier we build has its gain change when the output approaches the rails, and that looks like a nonlinearity. If that nonlinearity was just in feedback on its own, we'd be in trouble, because nonlinear analysis has been really hard from the start of the class, and this would probably be no exception. However, our nonlinearities tend to interact with a bunch of passive elements that are purely linear. And so maybe these will filter out the output of the nonlinearity somehow, and make our analysis tractable. So, on a wing and a prayer, we start our analysis by using Taylor expansion. So when we put a sine wave into a nonlinearity, we can imagine that nonlinearity is made up of a constant and an x squared term, an x cubed term. And that's going to result in a output sinusoid at the frequency of our input that's been scaled by some sort of gain that's given by the magnitude of this GD function, and some sort of shifted by some sort of phase shifted by some sort of angle that's given by the phase of this GD function. In addition to that, we're going to get a DC offset, and we're going to get harmonics. And both the DC offset and the harmonics and the amplitude dependence of GD all come from higher order terms of our Taylor series. If you have x raised to the n and you replace x with sine of omega t, that means you get sine to the n of omega t. And as you evaluate sine to the n of omega t using trig identities or complex exponentials, you'll find that it creates a component at sine of n omega t, which is called a harmonic. And by the way, the frequency omega is called the fundamental frequency because all of the harmonics are multiples, occur at multiples of that fundamental. Some of the sort of polynomial expansion of these sine to the n will result in terms that have a frequency of omega t, so those add on top of GD and give us this dependence on input amplitude, and some of them will come with no frequency, and that's where we get the DC offset. Okay, but finally we're going to make use of this L of j omega and assume that our loop is either low pass or band pass, which is generally true. And if that's the case, we can just filter out all of these harmonics that we generated. Now also, because our loop gain analysis tends to be small signal, we can just neglect the DC term. It's just some sort of offset in our output. So the upshot of this is that we can plausibly claim that putting a sinusoid through a nonlinearity and then low-pass loop dynamics results in another scaled and phase-shifted sinusoid of the same frequency. So the scaling and shifting happens through a pseudo-transfer function called a describing function. So GD is our describing function. And the major difference between it and a normal transfer function is that GD depends on the amplitude of your input. That's kind of weird, and it turns out to be really important. So there's a couple of ways you can think about how that works. One is that means that the poles of our loop gain are going to move around as our sine wave amplitude changes. So we can get dramatically different dynamics as the input gets bigger or smaller. Another way to think about it is this is a way of showing how our gain will be reduced as we approach the power supply. If we didn't have this dependence on A, then our linear system would have the same gain all the time. Here, now we can change our gain when our sine wave gets too big. So both of those capture the significance of having this amplitude dependence in our describing function. So let's look at an example of finding a describing function. We'll use this step nonlinearity to represent a super high gain amplifier. For our setup on the last page, we drive this nonlinearity with a sinusoid a sine omega t, and when we do that, the output is a plus or minus 1 volt square wave, because this nonlinearity is plus 1 when the input sinusoid is positive, and minus 1 volt when the input sinusoid is negative. We can express this output square wave as a sum of sine waves using Fourier analysis. Note that because this function is odd and centered at 0 volts DC, we have no DC term and no cosine terms, which are even functions. When we low pass that expression, we find that only the fundamental term, 4 pi sine omega t, gets through. And we know from the analysis on the previous slide that the coefficient of this fundamental term has to be equal to the describing function magnitude times A. There's no phase shift on our fundamental, which mercifully means that the angle of our describing function is just going to be 0, and that simplifies our analysis. So, rearranging slightly, we find that our describing function is 4 over pi A. And that's awesome because this describing function does what we promised. It makes it look like the magnitude of our gain decreases as the amplitude of our input increases. And that makes sense because no matter how big a sinusoid we put into this nonlinearity, our output square wave is plus or minus 1 volt. So our nonlinearity will scale up 1 millivolt sine waves but scale down 10 volt sine waves, and that's captured by having A in the denominator here. Okay, so let's see what this technique tells us about an oscillator in practice. We're looking at the phase shift oscillator from a few videos ago, and we can rewrite the block diagram for the phase shift oscillator to show that the first stage here is really a saturating nonlinearity. So it'll have a slope of minus r1 over 2 in its linear range, but if you hit either the negative supply rail or the positive supply rail, it flattens out and can't give you any more gain, no matter how big or small how positive or negative the input gets. The remaining loop dynamics are a third order low pass filter from the 3 poles that we have in the phase shift oscillator. And these other op-amps could nominally introduce nonlinearities, but because the gain on this one is higher, it's going to hit its rails first. So I've just kind of ignored the nonlinear behavior that these guys have hidden in them. We're not going to see it compared to the higher gain first op-amp. Alright, so this is a new nonlinearity. It's one we haven't seen before. It's different than the last page. So we'd have to calculate a new describing function to really nail our analysis of it. However, we can assume, and we're not going to do that, however, we can assume that the describing function will get smaller as the amplitude gets bigger, just like the one on the previous page, for much the same reasons. Because our nonlinearity maxes out at the rails of our amplifier when our input amplitude gets bigger than the rails, then the describing function forces it to clip at the rail levels, and that means that the describing function overall has to be inversely proportional to amplitude. And that's interesting because this describing function that replaces this nonlinearity is kind of in the position that a gain term would be in a root locus analysis. Like if you were trying to find the root locus of these three poles, you'd put just a gain of k here and then vary the value of k. So we know that when our input amplitude is small, our describing function is going to be large, and that will mean that we'll move far out on the root locus of this diagram, so our poles will shoot way off into the right half plane when we have a small input amplitude. And poles in the right half plane will cause that input signal to start increasing exponentially. So as the amplitude of this unstable system increases towards the rails of our describing function, then the poles will get, then the describing function will shrink, and the poles will get pulled back towards the j omega axis. And when the poles are on the j omega axis, if there's a perturbation that reduces our amplitude, the describing function gets a little smaller, pushing them back onto the axis. Or if there's a perturbation that increases our amplitude, the describing function also pushes the poles back towards the axis. Excuse me, when the amplitude decreases, the describing function gets larger, pushing them back to the axis. When the amplitude increases, the describing function gets smaller, pushing the poles back towards the axis. This analysis also tells us we're probably safe using a gain larger than 8 in our value of R1 and R2, which means that our poles would start on the right half plane rather than strictly on the j omega axis. However, as the amplitude of our oscillation gets larger, those poles will get forced back onto the j omega axis as the describing function saturates the gain. So even without finding this exact describing function and just knowing its kind of qualitative behavior, we can learn things about our startup behavior. We start with right half plane poles and they settle into the j omega axis. Our resistance to perturbations, the describing function will force the poles back to the j omega axis. And our safe range of gains, which is that we can probably go bigger than 8, but probably not smaller. We can also guess that we'll get more harmonics if we increase our gain, because it shortens the nonlinear range of this, the linear range of this nonlinearity, which is a neat fact too. So in summary, describing functions are transfer functions for nonlinear systems that rely on low-pass dynamics rejecting harmonics. Describing functions change with amplitude, so their poles are functions of amplitude of the oscillation. And saturating nonlinearities force poles back to the j omega axis in response to amplitude perturbations, which is captured by the describing functions being inversely proportional to the amplitude.